All right, so in this video, we'll continue our discussion on compound inequalities, but now we're going to look at OR compound inequalities. And this one's going to go a little bit faster than our last one. So here we have a definition, the union of sets A and B, written A union B. So that's how we say this, A union B is the set of elements that are in A or B or both. Stated using set notation, we have A union B is equal to the set of elements X such that X is in A or X is in B. Or you could say X is an element of A or X is an element of B. Now in mathematics, OR has the meaning it's in this set, or it could be in both. I always think of it this way. You want to combine the two sets. You want to take everything from set A, and to that you're going to add everything in B that you don't already have. So you're combining the two sets together. So when you're done, you're going to have everything from A and everything from B. And in some cases, there's numbers in both, but you're combining these sets together. All right, so if you look at number 7, if you union the two sets, I would begin by writing all the numbers down from the first set, and then I'll look at this is how I normally do it, and then I'd look at the second set here and look at and think, okay, what do I not already have? Well, I don't have the 4, the 8, or the 10. Notice 6 and 12, those are the multiples of 3. I already had those. So we're going to add to our set 4, 8, and 10. Now normally, if you left this as an answer, it's not wrong because it's still the same set of numbers, but we do normally put them in order. And that does help me out as your instructor when I'm grading. All right, let's look at number 8. So it says find or consider the following union. You have A is less than or equal to -3 or X is greater or equal to 2. So when we were doing intersections, we would have the intersection symbol, or we would have an and statement, and they essentially meant the same thing. And it's the same with union and or. We also call these disjunctions. So this is what we call a disjunction, an or statement. Remember, the and statements we called conjunctions. All right, so now it says a number is a solution to an or compound inequality if it is a solution to, oh goodness, I wrote the wrong thing here. It shouldn't say both inequalities. If it's a solution to at least one of the inequalities. Now remember, with an and statement, it had to be a solution to both in order for it to be true. So let's think about this. What if I gave you this disjunction or this or statement? Mr. Smith is a math instructor, or Mr. Smith is an alien. Is that a true statement? Well, yeah, because I am, well, at least one of these two things, right? I'll let you decide which. So as long as one of these statements are true, the whole or statement is considered true. Hopefully that makes sense when you read it. Mr. Smith is a math instructor, or Mr. Smith is an alien. So as long as one of those are true, the statement is considered true. All right, so it's the same with an inequality that's an or a disjunction. As long as one of the statements is, as long as the solution works to at least one of the inequalities, then it satisfies the disjunction. All right, so determine whether -1 and 8 are solutions to the inequality. So let's plug in -1. We have -1 is less than or equal to -3, and that's not true. Or -1 is greater or equal to 2. Well, that's not true either. So we don't have at least one of them being true, and so this is false. -1 is not a solution. All right, let's go ahead and plug in 8. Oh, and I got in the way again there. So we have 8 is less than or equal to -3. or 8 is greater or equal to 2. Well, 8 is not less than or equal to -3, but 8 is greater or equal to 2, and so this is considered a true, or it is a solution because it works in at least one of the two statements. All right, so this is true. Boy, and I made a mess of things there. So 8 is a solution. So again, with and statements, in order for that statement to be true, or like with inequalities, the value is a solution if it works in both. Otherwise, it's not a solution. With or statements, it only has to work in one of the inequalities to make for it to be a solution. All right, let's move on to our last page. It says graph the solution set for the inequality, then write it using interval notation. So we have x is less than or equal to -3, or x is greater or equal to 2. This is the compound inequality we were just looking at. What does our solution really look at? Or what does it look like? So let's go ahead and graph these. We have x is less than or equal to -3, which is basically all the numbers from -infinity to -3, where we have a bracket at -3. And then if we graph x is greater or equal to 2, we start at 2 and we go forever right. So now remember, with an or statement, we're basically combining these two sets together. We're going to union them or combine them together. And so when I put these two together, then we're just combining the two sets, and you can see this is like the opposite of what we had with and statements. Normally our solutions were everything in between two numbers, whereas with an or compound inequality, you normally get everything on the outside of two numbers. So that's what you're normally expecting, unless you have some kind of special case. All right, so don't forget, we need to write this in interval notation. So going from left to right, we start out here in -infinity land. Eventually we get to -3, and then we're going to union that with the other part of the set. It starts at 2 with the bracket and goes forever right. In fact, we have a bracket on the -3 and the 2 because of the equal sign in our inequalities. The endpoints are included in our solution. All right, so let's go ahead and look at number 9. It says solve each compound inequality, write the solution using interval notation. All right, so just like we did with and statements, we're going to solve each of these separately. So I'm going to add 4 to both sides here. So I have x minus 4 is greater than 2. We add 4 to both sides. We get x is greater than 6. And then on the next one, we have -5x plus 1 is greater than 11. So we're going to subtract 1 on both sides. We get -5x is greater than 10. And then we need to get rid of that -5, so it's -5 times x. We'll do the opposite and divide by -5. Now notice we're dividing by negative, so we have to flip that symbol, and so we get x is less than -2. So our solution is x is, and I'm going to put it in order here, or I should say I'm going to put the smaller number on the left, the bigger number on the right. We have x is less than -2, or x is greater than 6. All right, so if you look at what we had above, it looks quite similar. And so if you think about it, x is less than -2, that's going to be everything to the left of -2. X is greater than 6, that's going to be everything to the right of 6. And so this is very similar to what we just did up in part B there. And so, it's not a bad idea to graph these, especially if you're not quite sure what your final solution should look like or how you should write it in interval notation. So we have x is less than -2. We've shaded everything to the left of -2 with the parentheses since there's no equal sign here. And then, or x is greater than 6, so that would be parenthesis and everything to the right of 6. All right, so that's our solution. So we have -infinity to -2, parenthesis, union 6 to infinity, also with a parenthesis at the 6. All right, last problem. So actually, I would encourage you to try this one, and I would just warn you, you're going to run into something a little different. Let's see what you come up with. All right, so let's see how you did here. So we have 4x plus 5 is less than or equal to 5. We're going to want to subtract 5 on both sides first. So we get 4x is less than or equal to 0. I'm trying to get x by itself, so I'll divide by 4. And 0 divided by 4, that's 0. So we get x is less than or equal to 0. On the other side, we're going to subtract 4 on both sides. We have 4 minus 2x is less than 10. So subtracting 4 on both sides, we get negative 2x is less than 6. So we're going to divide by negative 2. Again, we know with inequalities, if we divide by a negative number, we have to reverse that symbol. And so this becomes x is greater than negative 3. All right, so I'm going to put my x is greater, so we have x is less than or equal to 0, or x is greater than negative 3. That's our solution. But I really want to have the x is greater than negative 3 on the left because negative 3 is smaller, and we have x is less than or equal to 0 on the right. Now, if you look at the other ones that we've done, it looks like the signs are not facing the same direction. So I would recommend, it's not a bad idea with all of these to actually graph your solutions to make sure that they make sense. And you can see something's just not right here. X is greater than negative 3. We're expecting normally with our smaller value to shade everything to the left. But if it's x is greater than negative 3, we would be shading to the right. So let's go ahead and graph these. We have x is greater than negative 3, so that's a bracket at negative 3, and you shade everything to the right. And then we have x is less than or equal to 0, and so we're going to have a bracketed, oh no, that's, I think I did that right, wrong. Let's see. No, that's, let me fix this. This is a parenthesis, and the other one should be the one that's a bracket. So parenthesis, negative 3, we shade everything to the right of that for x is greater than negative 3. And for x is less than or equal to 0, we shade, or we put a bracket at 0 and we shade everything to the left. And now if you look at these two, with an OR statement, remember we're combining the two sets together. Well, when we combine these two sets together, what do we get? Don't we get everything? And so that's all real numbers. That's how we would say that. And we would write negative infinity to infinity. All right, that's it for this video.